I want to point out, though, that in 2008 and 2011 was the first time there was a statement made that there was sufficient evidence of an association from the population health research. Enough research had been done of sufficient quality to show that there was an association with the development of asthma for people who live in chronically damp conditions, which likely have a dysfunctional microbial ecology that's associated with that chronic dampness. So for the first time, we really have major publications and highly regarded researchers saying there's sufficient population evidence to show this connection. At that time, actually, a couple of major organizations, including the American Industrial Hygiene Association, came out with position papers on moisture and dampness. And actually, ASHRAE started an active conversation about a position document on mold and dampness. The point being, there was sufficient evidence to drive policymakers and advocates for building management that you should have an aggressive approach and policy towards managing moisture in your building. And AIHA advocated for a 48-hour response time to moisture problems, that all facility managers should have policies that address moisture in that time frame, based on what we now know about so many health conditions.
So I missed, what year is it? Said there's development of asthma rose to the level.
Well, WHO had, they felt sufficient literature to show an association with the development of asthma. Again, this is in sensitized individuals. And then Mendel just said there was even more robust research to support that. Well, then in 2015, there was an additional review, and this is to show you even more robust evidence. So I left all of this in instead of just focusing on the dampness piece, but they looked at environmental exposures and asthma. And you know, we talk about asthma a lot, and the reason we talk about asthma a lot is because 10% of our population, roughly, just under 9, roughly 10% have this disease. 1 in 10 of our population have this chronic respiratory condition. That's an epidemic. That is an incredible portion of our population. And 20% to 25% of people have some kind of allergy. And most of the allergens we know out there, roughly 25% of the population has an allergy to that given allergen, whether it's dust mite or pollens or different kinds of molds. From this systematic review, sufficient evidence of a causal relationship, so the evidence is there. If it wasn't before, now it's more robust. Specifically, we've known for quite some time, clear back from the year 2000, we've known about a dose-response relationship with exposure to dust mite and actually the development of asthma as well as the exacerbation. We know chronic exposure to dust mite allergen results in the development of the disease in sensitized individuals. Cat allergen in this recent literature rose to this level of association, causal relationship, and roach allergen exposure, which primarily occurs in urban areas. But we know exposure to these allergens over time, there is a causal relationship, and that's a huge rise in the level of the evidence. That's one of the hardest things to make that connection, and why you see a lot of resistance from the cognitive sources out there about whether to say this causes a health effect or not. Is there enough evidence, robust evidence through good research to be able to support a causal relationship? If I see this in a building, it causes this. So and there rightly should be a high threshold to reach that level of evidence. But that doesn't mean in individual cases that you might not see a exposure that's leading to something that you can advise and help a client. But to get the research to that is often very difficult. For these conditions, there's sufficient evidence of a causal association. So that says that the literature, the quality of the kinds of research that can be done is not of a type that can show that causal relationship. It's usually population research. It's usually, we're not setting people down, blowing mold into their face, and then seeing if they have a health effect. We're asking questions typically retrospectively. You grew up in a home, was it damp? Did it have this condition or that condition? And then ask those people, what health condition do you have now? Do you have a disease or not? And then you can do a statistical analysis and show a sufficient portion of that population actually has this disease as an outcome from an earlier exposure. So a lot of these studies are based on that kind of evidence.
If we narrow it down to a large area, there are two types of odor confirmation tests that we can do. The large area really is isolation. You know, if we think it's this wall, we think it's this carpet, we think it's this ceiling, you know, what we do is we take tape, we take visqueen, we tape it, we want that to be airtight, and then there's generally a little bit of head space. There's going to be some air space in there. We can allow a certain amount of time to pass, or if we wanted, we can heat that area a little bit. We can raise the temperature in the room. We can smell the head space. The second is what we call a small area patch test, and this is very, very effective. And this involves using aluminum foil, a napkin, and painter's tape. And what I did is I drew a picture over on the wall here. So your outside edge is tape. This is aluminum foil. And then this is a napkin. And by using the blue painter's tape, we can pretty much stick this on any type of surface or any type of material. And if we wanted, we can even warm it up a little bit with a hairdryer. And what we're trying to do is draw the odor out of a substance or out of a surface into that napkin. And the beautiful thing about the aluminum foil is once we detach it, we can crumple it. Now we've trapped the odor inside, and we'll take you through the process of what we would do next. In order to do this, I like to use, they have aluminum foil sheets, and what you want to do is you want to get a sheet that's slightly larger than the napkin that you're going to use to absorb it, and then painter's tape. In terms of sniff testing, a lot of times I like to do dual testing where I'll smell it myself, and then I want someone who is familiar with the odor to smell it. This testing needs to be blind. You don't want to know where it came from. You don't want the person that's the identifier to know where it came from. They're going to be sniffing multiple samples that were all taken in the building, but I want a blind sample. And so we're going to do the identification, sniffing either outdoors or in some sort of clean environment. I've done it a lot of times in my car, for instance, with the client. Some of you may deal with fire-related smoke odors, so we have some tips in terms of where the odor problems are going to be there. Typically, HVAC systems, ceiling voids, wall voids, restored contents. Some of the questions that I'll ask in these situations is I want to determine whether or not it's a construction problem. I don't ask the customer that, I'm asking myself this. Is it a construction problem? One of the things that contractors will do is oftentimes if they don't provide the smoke odor removal services themselves and they subcontract that, what they'll do is they'll try to save the expense if they can. So a lot of times they'll figure, well, if I demolish and if I remove everything, they use demolition as a method of odor removal. So they tear out what they think needed to be torn out, sometimes a little bit more, and then they don't deodorize. And what happens is they'll leave large openings in the exterior of this home or building. So there's a lot of air that passes through. They don't realize it smells. All of a sudden they close it up and they redecorate and they turn on systems, and all of a sudden now we have a smoke odor problem that we didn't have before. It can be difficult.
So the rules to get there, this will sound familiar. I tell people there's 5 priorities: air seal, air seal, air seal, then we'll insulate, and then we'll put in HVAC. If the house is not tight, all bets are off. I can't control it. And then also I assume water tightness to begin with. I love what Joe Stiebrick says. Like if you can't keep the water out, you don't have a building. You have the outdoors. This is something that ends up probably doesn't show very well. This is how you know you're a geek. You do a gingerbread house and you put the stack effect on it. So who here knows the stack effect? Okay, good. So most of us. So basically, if a house is leaky, it comes in low in the house in the wintertime, rises, and then comes out. If you can stop the top and the bottom leakage, you can largely arrest the stack effect. It's not perfect, but the top and the bottom are what you really have to play with. Exactly. It's still there, but there just isn't a lot of pressure on it. So in testing this house, blower door testing, this is the actual picture from the house when I was doing the test. It's about 2,500 blower door. It's in cubic feet per minute at 50 pascals. The house is about 2,200 square feet. In doing the testing, I found out that for the stack effect, the top and the bottom of the house were quite well sealed. Not perfectly, but just not enough to justify going in and doing more. And I'm not afraid to go do more, but this house didn't need it. It actually broke the energy model. The energy usage was so low when we put in what actual usage was and put it in the energy model, we couldn't get them to go. We actually had to model it with insulated walls to get it to match. This is a good rule of thumb. So for everybody here, you may hear ACH 50. I actually don't like ACH 50 because you have to do a calculation. You need to figure out the volume of the house. If you ask 3 different people for the volume of the house, you'll get different volumes. Blower door number is raw. Square footage is raw if you use like the county records. If you get the square footage and the blower door basically equal, I find that's adequate for control. Sometimes 1.5 will work, sometimes you gotta be 3/4, but 1 to 1's a good rough rule of thumb. This house is 2,500 to 2,200, so it's a little over 1 to 1, good enough, which told me that the solution to the house is HVAC focused, not building shell focused. So what we did with this is going to be very familiar. I wanted to pressurize the house because I know there's garbage in the walls because we got headaches. Want to dehumidify the snot out of the thing. They were actually running 42 to 44% relative humidity with 70-degree dew points outside. We dried the heck out of this thing. The client told me her sinuses were drying up and she was starting to get dry skin in August. We had some dryness, so we could do that. Pressurization requires fresh air because you have to add air to pressurize it. So that just comes in. Continuous filtration, they already had a MERV 16 in their system. And then we use a ventilating dehumidifier, same stuff that John uses, and that has good filtration. And then the last thing though is load matching. So at any given moment of time, a house needs a different amount of heating and cooling to keep it warm or cool, whatever you're trying to do. If it's cold outside, you need more heat. If it's really hot outside, you need more cool. But for the most part, things are pretty, you don't need a lot. So you want the smallest equipment you can get away with to add a little bit of heat or a little bit of cool.
They knew they wanted something that was both quantitative and qualitative, and they were looking at it from a cost perspective of, am I going to have to, if I have to test the airport every, 15 minutes, 30 minutes with a cassette filter and then throw it under a microscope, and how am I going to do that, right? So these were the objectives that drove the research, if that makes sense, right? Research, that's why we went off and sailed for the New World. And where we landed was someplace that we'd been before. So in the early 1900s, there was this thing called fluorescent microscopy, right? And it basically was working on this principle of biofluorescence. I'm just going to give you the idiot's guide real quick. It goes like this. If you hit a particle with invisible light, based on what the particle's made of, it will throw visible light back at you. Okay? And depending on what color it is and how much of that light energy comes back, it gives you information about what that particle's made out of. Okay? And some guys in Germany in like 1911, depending on Teague's credit, figured this out and they started working on it. So there, you can go out and you can drop some serious coin and buy a fluorescent microscope. And you can do that with a static microscope. Now, if you go into a medical lab, you'll run into these things called cytometers. Cytometers are essentially electric, kind of automatic microscopes, right? And they use them for blood work a lot. It's basically a microscope that uses an automatic counting mechanism instead of a human, right? So what this box is, if you really want to know what this is on a technical side, from the research standpoint, the UK Ministry of Defence said, well, why don't we take a cytometer and a fluorescent microscope, put them in a room alone, play some nice music, let them have a baby, and kapow, all right? And what we end up with, this in 2012, that's what I tell people is this is the combustion engine and the Instascope is the Corvette, okay? So the combustion engine is that geeky looking thing down there. Essentially what happens is we suck a particle out of the air. We send it through a chamber. We hit it with light across different wavelengths. You can see excitation wavelengths and detection wavelengths and blah, 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 blah. Here's what we do, right? We hit it with different energies of light. We see what comes back at us. We take that data and we take size, fluorescent response, and fluorescent intensity, along with some other phenotypic stuff that I'm not going to get into, and we get a fingerprint. Right? And the easiest way I can describe this is if I'm looking around the room, I'm going to say, you have blonde hair with a white sweater, you have white hair with a blue sweater, you know, you're sitting lower, and so I'm taking size and color dimension, and that's my optical way of recognizing between you guys. That's essentially what this thing is doing, is it's taking optical data to create differentiation. Okay? So it's not just how many. That's a particle counter, and we do that. We built that in there. How many is one thing, but this is answering the question of what kind, okay? And what kind is really valuable information. So there's a lot there. There's peer-reviewed paper on biofluorescence aerosol cytometry going back 25 years. Okay, because that's when they were starting to mess around with this and publish this, mainly in the atmospheric space. One of the things I said to Joe was, the bridge is broken, right? In academia, this is a known quantity. Quantifying PBAP, primary bioaerosol, blah, blah, blah. Quantifying what's in the air with aerosol cytometers, biofluorescent aerosol cytometers, this is not news. However, if you go to some place like AAAR, the Academy of Aerosol Research, you're going to see papers are flowing out of universities now using the research version of this tool, which we built and sold for $150K. The problem is, to use the research version, you need to be able to interpret particle by particle data. So it's made for researchers. Guys come to me and they're like, can I buy, it's called the WIBS, the research version. I'm like, you can buy it and you can use it as a coffee table unless you're feeling like, you know, doing some postdoctoral work. So here's what we did. We took this tech, and my job, just to, you know, rat myself out here, I'm not a scientist, okay? I was trained as a musician. So, what's that? I was a classical guitarist, right? So that's the world that I lived in. And so my job in the company for the last 5-6 years has been to say, I don't understand, make it easier. My mom wouldn't want to buy that, and my mom doesn't understand. That's been my job, is to take this super geeky stuff and make it accessible to normal guys who do real work in real houses, and make it accessible to folks. That's what we're trying to do. So here's what we did.